paper. No, not select. Yeah, right, select papers. Not select, I need this one. This is lambda 3. For your own sake, this is lambda 4. It becomes messy as you go. We don't have a recursive formula. But the beautiful thing is that it's an exact averaging. Any questions so far? So when you truncate the series, remember when before, actually, the classical averaging theory just gives you the first term. And we know that the solutions are close to each other in order epsilon, because this term is indeed multiplying by epsilon. But then if you add the second term, we know that the two solutions are close in order epsilon squared. And if you include the third and fourth and so on, so it increases your accuracy. Okay? So I may not have time to give you an example, but it's really straightforward, doesn't need an example. I'll show you one result from our recent paper. This is this curve. It's worth discussing. So this is the Kapitsa pendulum kind of thing. Okay? And we applied higher order averaging after variation of constants formula. Okay. So again, please, very good. Okay, anyway, that's good enough. So what is this? This is the error in the stability boundary between the exact thing and higher order averaging. The blue is the first and second, because when you apply for the Kapitsa, the second lambda 2 vanishes. Okay? The thing that I want to mention is that the first order averaging is just lambda 1. Second order averaging is lambda 1 plus lambda 2, right? Third is lambda 1 plus lambda 2 plus lambda 3. And each lambda is divided by factorial. Okay, so lambda 2 was 0, so first and second are the same. Here's the third, fourth, and so on. So first of all, you can see the following. This is omega, okay? This is omega. So the higher you go in omega, the smaller the error you get in anything, which is the main concept behind averaging. So if you want a first order averaging to work, for sure it will give you any level of error you like, but you just need to go high enough. This high enough frequency may not be feasible for practical applications. So higher order averaging allows you to ensure stability with smaller frequency. So I'm trying to say, if you wanna meet a certain error level between the average dynamics and exact, say 0.2%. The first order averaging will meet it here. The second order averaging or the third order averaging will meet it there. So you can achieve stabilization at smaller and smaller frequency, making it more feasible for practical applications. So two things from this figure. Higher omega, the smaller the error for any average dynamics, for any higher order averaging, it doesn't matter, any order of averaging. And for a given level of error, of course, higher order averaging will meet that level early in omega before the first order averaging, right? Because you're adding more and more terms. Theoretically speaking, if you add all the terms, you have exact result. The error will be 0. Okay? Any question about that? Yeah, we're done. I may any question? you have any question? So I will just, I refer to try to see what we had so far. So this is what we learned. What we knew what is a manifold, like some language, a manifold, what else? Tangent vector, right? What is tangent space, TPM? What is a vector field? What is a Lie derivative? What is a Lie bracket? Push forward. Right. This is the language that we learned. This is the language. How useful it was to us as a language. Well, it allowed us to get the benefit from these results. Frobenius theorem, right, for integrability. Integrable if and only if what? Anybody remembers? Involutive. Very easy to remember. Then go back and check what is the definition of involutivity, that's fine. So Frobenius, the orbit theorem, so actually the language also add to the language the orbit of some family of vector fields through a point x naught, the orbit theorem, so we know that the tangent space, the set of admissible velocities, this is the set of, you can think of it as reachable points, but more than reachable points. The set of reachable points, so the tangent of it is the set of reachable velocities of attainable velocities. It gives you your ability, just the Lie brackets. So this is your ability. What are the set of velocities that I can ever generate is just your Lie brackets. So this by itself immediately gives us a criterion for accessibility, right? Because you know your ability is just Lie brackets, and if you want to cover the entire tangent space to get accessibility, so this means that accessibility requires, and it's if and only if the log, that this guy covers the tangent space. So we can talk about nonlinear properties here, and then we extend it to small time local controllability. It's accessibility plus additional things, right? So here we talked about good and bad brackets. We talked about control reversal, if you remember the example in the homework. We talked about recurrent vector fields, and I'm very glad that some of you guys, in the example of the rigid body, some of you got it. So the rigid body, there was a bad bracket that cannot be neutralized. So it precludes small time local controllability, but there is still a hope to get controllability, not small time, if your flow or if your drift vector field is recurrent. So whose flow is periodic, and it was indeed the case. So we could conclude full controllability, but not small time. So we had this, and from the language of controllability, of course, this was immediately useful for characterizing the non-holonomic constraints for a mechanical system. If you give me any Pfaffian constraint, I can judge if it's holonomic or non-holonomic, if it's integrable or not. And after characterizing controllability, we talked about motion planning, right? So this is motion planning. Talked about the chain system, so this is using sinusoids, steering using sinusoids, chain systems. We also talked about Lafayette. It's hard to remember. And Sisman. Steering using piecewise constant controls. Then we went to mechanical systems, which necessitated extra language. The Riemannian metrics, covariant derivatives, Nabla, geodesics, Q, K, double dot, gamma, I, J, K, Q, I dot, Q, J dot. How to get the gammas from the Riemannian metric, and more importantly, the relation between mechanics, geometry, and optimization, right? So a mechanical system, the equation of motion are just the geodesic, which minimizes the action integral, right? So then, having developed this language of mechanical systems, we indeed considered mechanical systems or mechanical control systems. Now we have control; these are free mechanical control systems, and we consider the hard case without potential function. Why? Because when you lose your potential energy, if there is no potential energy, so the linear tool will always say that the system is uncontrollable. So you cannot use just common linear controllability. So systems on the form of, nabla gamma prime, this guy is just summation j of 1 to m y j of q uj. The controllability of such system relied heavily on what we call the symmetric product, right? Which can generate acceleration, can generate forces. Then what else? We talked about feedback linearization. State feedback linearization, so you linearize the entire system, and output feedback linearization, so just part of the system. So this is related to the relative degree concept, how we extend it from linear, the difference between numerator and denominator degrees, to nonlinear, relative degree. So how many times you're going to differentiate your output function until the input appears. And this was also related to the concept of zero dynamics and its relation to the concept of non-minimum phase or minimum phase. And again, it's an extension from the linear system theory, minimum phase. So in linear system, it's the zeros should be in the left half plane, no zeros in the right half plane for minimum phase. And here we extend it to nonlinear systems. You get the zero dynamics and check that it's stable on its own. Then we talked about nonlinear stabilizability. Broken necessary condition. And then we move to Floquet, averaging, variation of constants formula, chronological calculus, what we have today. Exact averaging, or complete averaging. So this is our course. Last year we didn't have the things in, we didn't have this, we didn't have output feedback linearization, we didn't have chronological calculus. So I'm glad that we covered them, thanks to the content and dynamics, so we can squeeze things. Anyway, any question about any of these? Any question? So done. This is the last lecture. One thing, please go and do the what's called the course evaluation, because it's very important for us. We, based on that, we decide whether to continue giving this course or just abandoning it for all. Or so please take it, particularly if it's a small course. If it's 100 students, that's fine. There's going to be always some students doing it. But 8 students, actually, if less than 5 did it, it will not show up. It will just be as if nobody at all did it. So please go and do it. Okay. We will have.